Hello and welcome back to Algebra 1. Chemistry. But it's going to feel a lot like Algebra 1. Okay? You're just going to be solving for that one variable in a formula. Easy breezy, right? Okay. Well, long time no see. I'm going to start this lesson before I introduce you to those formulas, and there's going to be 3 formulas we're going to use this module. By the way, module 12. Okay? I want to bring this back from module 11 that we talked about and just kind of review this a little bit. Let me kind of turn this down just a little bit so you can see it better. Okay, so we have here a phase change diagram, and it's almost like stair steps if you think of it like an incline with a step, and then you go up to the next step, okay? So when you're at the very, very bottom, like at the very bottom of the steps, that's where you're the coldest. So as far as phases go, you would be a solid. You would be like ice if this was water, okay? So down here in the very bottom of the steps, you are a solid. And if you're water and you're ice, that means you have to be below 0 degrees Celsius, right? So that line that represents solid is all below 0 degrees Celsius. Now, as we add heat energy by either, setting the ice cube out on the countertop and letting it start to absorb heat just from the surroundings, or maybe we throw it in a frying pan, who knows? Anyway, we're going to give it it's going to be absorbing heat energy. And as it does that, the temperature of that ice starts to rise. It goes from maybe -20 to -10 to -5 to -4, 3, 2, and then finally it's 0, okay? And when it hits 0, this is when we get our first phase change and that ice starts to melt, right? So we're melting here, and this is a process, and we have to, it doesn't just happen like that. As you can see, it's a process, and it requires heat energy. So as we move along this axis, we're still adding and absorbing heat energy to melt that ice, okay? Now, notice that the temperature, though, stays constant. It like plateaus, like a flat plane there, meaning that while that ice is melting, it's not getting any warmer temperature-wise. It's just using all that energy to melt, okay? When the melting is finished, then lo and behold, we have liquid. And we stay a liquid, a really cold liquid, because you were just ice a few moments ago, right? And you start warming up. And as you can see, as I start climbing this hill, my temperature is increasing as I am. So we're kind of going up at an angle. My temperature is increasing and my energy is increasing. And it keeps doing that and absorbing more heat energy and getting warmer and warmer, until we hit that liquid water reaches 100 degrees Celsius. And at 100 degrees Celsius, we start to vaporize or boil that water and turn it into steam. So again, we hit another phase change, and that is represented as a flat area. So once that water gets to 100, we go through the vaporization process as we cross this like little flat bridge. And again, we start it as liquid and we end it as a gas or steam. In order to cross this bridge, obviously it takes heat energy to move this way. But do you notice again, the temperature is hanging out right at 100 flat all the way across because it's using that heat energy to vaporize it and convert it into steam versus using that heat energy to make it warmer. And then once the process is done, we have a gas and the temperature starts to climb again. So I wanted you to understand this. And now what I want to do is I want to talk about parts of this curve and different formulas that we use depending on where we are on the curve. So the first formula I want to talk about is the one that we use when we are traveling uphill or downhill. So all these inclined places here, from here to here, from here to here, and from here to here. Notice, I'm not talking about crossing the flat areas, right? We're not talking about making it across the plateaus. We're only talking about climbing the hills as a solid, climbing this hill as a liquid, and climbing this hill as a gas. Those are times when you are still the same state from here to here. You're still a liquid this whole way, but your temperature is increasing. So you're having a change in temperature, but you're not trying to melt or vaporize, okay? So for that, we're going to use for all the uphill and downhill. So please know that anytime I'm asking you to find out how much heat it takes to change the temperature of like a liquid, a solid, or a gas, I'm not asking you to melt it. I'm not asking you to vaporize it. I'm just asking you how much heat it would take to make one of these substances warmer, okay? Then this is the formula we're going to be using. So let's talk about this real quick. Q, by the way, is what we represent heat energy. So anytime I ask you how much heat energy, you are solving for Q. And this formula always spits out Q, heat energy, in joules. That's a new unit that is for energy. So heat energy is Q, that is the Q that you're solving for, and it comes out in joules. It goes in and out as joules. Now, let's come to the other side of the equation. The other things that determine the amount of heat you need is, first of all, the mass, and the mass will always be in grams. So if you remember that, now we've talked about that a lot, so whatever number is followed by the G or the grams, you need to know that that is your mass, and that's going to go here. Now, specific heat, first of all, know that that is a different kind of heat than this. When I'm talking about this one, that's CP, I'm going to call it specific heat. Specific heat, not just heat energy, okay? They're two different things. This is heat energy, this is specific heat. Don't get them confused, okay? This is basically a constant. You may be asked to solve for it sometimes, but for the most part, all the time, if you're asked to solve for something else, it will have to be provided for you. It's nothing that, it is a constant, okay? So specific heat, and I'll talk about where you find those in a minute. The next thing is the temperature change. So this is a delta sign. The triangle means change in temperature. And I know that's got a little curly on it. It's not, it's just a T, okay? So I didn't mean to put the curly on it. So this is temperature change. So if I tell you that I went from 10 to 30 degrees, that I warmed up some water, it started at 10 and it ended at 30, then the difference, the change, would be the difference between those two numbers. Now, the way we should always figure it out, and I forgot to finish writing that word, is final minus initial. Final minus initial. So if I say it went from 10 degrees to 30 degrees, the final is 30, minus the initial, which is 10. 30 minus 10 would give you a change of 20 degrees. So you're plugging in the change, how much that temperature went up or how much that temperature went down. Before I leave this formula, I want to go back to this specific heat real quick and show you where this can be found. If you look on your reference table, we'll talk about water first. So water, if you look right here, it says the specific heat, right there, specific heat of water, okay? Specific heat of water. It gives you the little symbol, CP, right here. And it gives you 3 values. The reason why is because water can exist in 3 states. So if I tell you I'm trying to warm up liquid, then you're going to need to pull the specific, and you need to plug in the specific heat, then you're going to need to pull in the water value, the liquid value. If I tell you I'm trying to bring, let's say, take a block of ice that's like -40 and warm it up to -10, it's still a block of ice, but it's got a warmer temperature, then you're going to use the specific heat for the ice. So all of your waters, whether it's solid, liquid, or gas, if it's a water, will be right here that you'll plug in for the CP. If it's a metal substance that I'm heating up, like iron or silver or whatever, then there's right here, there's a list of all the metals that I would expect you to use. And again, in this first column is their specific heat value, okay? So specific heat, if it's not provided to you in the problem, it is a constant that can be found on this page, okay? All right, so what we're going to go to now is we're going to talk about, so this formula, if you remember, it only covered the parts of this where we were going uphill or downhill. So you got to be going up, 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 right? Or down, down, down. You can't be going straight across and use this formula, okay? This is only for uphill or downhill with a change in temperature, right? That's when you know to use this one. So what if, though, I wanted to know the heat that it took to melt something or to vaporize something? Do you agree that there's no change in temperature if I'm melting? Do you see it just hangs out at 0? This hangs out at 100. We're not changing the temperature if we're melting or vaporizing. So we can't use the formula that says change in temperature because there ain't none. So we need a different formula for those two circumstances. So let's talk about melting. This, my friends, is the melting formula, okay? Now, I hope you know that it requires some heat to melt some ice. If we're going to melt something, it takes a certain amount of heat to do that. So how do you know how much heat it takes to melt something? Well, the fancy word, the scientific word for melting is fusion, F-U-S-I-O-N. Fusion. So the heat of fusion is the amount of heat it takes to melt something. So if I want to know how much heat energy, anytime that says that, you're solving for Q in joules, does it take to melt something, okay? Melting, then I'm going to pull this formula, and it's going to be the mass in grams of that block of ice I'm trying to melt, times, again, another constant, the heat of fusion, which happens to be 334 joules. It is a set constant number. And just to show you here, the heat of fusion, you can see that little HF right there, is 334 joules. That's where that comes from. So when you know you need to plug in that to solve for a melting problem, then that's where you get all of these numbers that we're using today in these formulas. Specific heats are here, and so far the heat of fusion is here too. Okay, so you're simply going to, anytime I ask you about finding out how much heat it takes to melt ice, to find that heat, which is Q, you're going to take the mass of that ice times this number. Okay? All right. Now, what if I want to vaporize something? Well, we're going to basically do the same thing, right? The only thing is it doesn't take 334 joules to vaporize something like it does to melt something. So for vaporization, we need another number here because it doesn't take the same amount of heat. So if I want to know how much heat energy it takes to turn some water into steam, which we know it does take heat energy to vaporize water, we're going to take the mass of that water we want to vaporize in grams and times it by the HV, which is heat of vaporization. This is a different number. That's 2260. All right. Again, that number is right there. Heat of vaporization of water, HV, is 2260. All right. So just that simple, you just plug in and solve for the one thing that you want. What I do want to talk about before we start working problems is I do want to talk about, in all of these formulas, I say that heat is expressed in joules. So anytime you solve for Q using any of these formulas, your answer is going to be in joules. Well, that's fine and dandy if a number doesn't get too big. But if you deal with a really big number that you get for Q, like let's say 50,000 joules, then I might ask you to give me that amount of heat in kilojoules. So how do I change this big amount of joules, like 50,000 joules, and express it in kilojoules? All you do is divide by 1,000. So 50,000 joules is the same thing as 50 kilojoules. So instead of having to deal with really big numbers, I might ask you to express the answer in kilojoules. And again, you would just divide that big amount of joules by 1,000 to change it into kilojoules. All right, so I think we should work a few problems. Why not? Okay, so why don't we start with, I got 4 problems. I'll go ahead and tell you. So this video is not going to be as long as the last one. 4 problems. That's it, I promise. All right, so how much heat energy? Now, do you remember heat energy is the Q, right? Heat energy is the Q. So I am solving for Q. How much heat energy, right? But there's 3 Q formulas, so we got to figure out which one. Is needed to raise the temperature of 15 grams. Grams, remember, is mass. And we want to know how much heat it takes to raise the temperature of 15 grams of liquid water from 10 degrees to 28 degrees. Well, do you agree that if I warm some water up from 10 degrees to 28 degrees, that I'm not trying to melt it, I'm not trying to vaporize it, I'm just trying to make it warmer. This is our change in temperature, all right? So when you go back and you think about your formulas, which by the way, if you haven't noticed already, all your formulas are here, and the Q formulas are right here, and this tells you what all of these letters stand for. Okay, and then again, remember your constants that you need to plug in for heat of fusion, heat of vaporization, and specific heat are all on the front cover where the constants are. Okay, now, because I'm solving for Q, I have mass, and I need a change in temperature, there's not but one of these formulas that's got delta T in it. There's not but one of these formulas that has temperature in it at all. So when I see temperature and I'm solving for Q, then that automatically lets me know I need to use this one, right? I got to use this one. Easy enough? All right, so what am I solving for? How much heat energy? That means I'm solving for the Q. So I have to plug in a number everywhere else. If it's not given to me in the problem, then that means it must be one of those constants that I need to get off the front cover, okay? So remember, M is your mass, and it tells me my mass is 15. So in this M spot, I'm going to put 15. Now, specific heat. Nowhere in here does it give me the specific heat. This is the change in temperature, all right? This is not heat. Temperature is degrees Celsius, Kelvin, all that. This is temperature, okay? I don't know, my specific heat is a constant. So I say to myself, this is liquid water. So I go to the front cover and I find the specific heat for liquid water. And it says right there, the specific heat for liquid water is 4.18. So in this spot, I'm going to plug in 4.18. That brings me to the change in temperature. Change in temperature. This is one thing we're plugging in, change in temperature. It went from 10 to 28. Again, if I say the final minus the initial, that gives me 18-degree change. So the temperature went up, it changed by 18 degrees. So I have everything plugged in. So I am going to just simply multiply these three. 15 times 4.18 times, 4.18 times 18. And I get 128.6. All right? So remember, anytime you solve for this, I know that that is joules. If I use this formula, that is joules. Now, that's kind of a big number, right? I mean, we're in the thousands here. So I might ask you just to tell me how many kilojoules that is. So if I divide this by 1,000, oh, by the way, you can just Beyonce it. Now, I don't know about you. Anytime I can Beyonce anything, I'm going to do it. And that just means I take this decimal and move it to the left. Move that decimal 3 places to the left. Bow ya! So I get 1.1, and I'm going to round that 2 to a 3, and then that would make it kilojoules. Okay, you can divide, if you want to divide it by 1,000, you go right ahead. I'm going to Beyonce it. Why not? Okay, so 1.13 kilojoules. Okay, let's move to a different one. Again, only 3 more. This is not a long 45-minute one. Okay, this is going to be a quickie. All right, so let's do this one. Calculate the specific heat. Whoa, that's not heat energy. That's not Q. Specific heat is that CP that I normally get off the front cover, but they want me to find it. Okay? So why can't I just cheat and look it up? Well, because they said this was a substance. They didn't tell me which one. So I can't just go look up on the thing and say, okay, because nowhere on here does it say substance. You got it? So that means they're wanting me to find it. They're not telling me what it is so I can look it up. So I'm calculating the specific heat, which is the CP, right? So I am looking the CP. That's my, I don't know. For a 20-gram substance, this right here is my mass. It said it absorbs 2,500 joules. Joules is my Q, remember, of heat. So joules is the heat, that is my Q, and it increases its temp by 12 degrees. So this time I didn't have to subtract final minus initial. It didn't tell me that it went from like 10 to 22. It just told me it went up by 12. The change is 12. I didn't have to subtract to find it. So this is my change in temperature. So, of the 3 formulas, again, I'm not melting, I'm not vaporizing, so I'm going to use Q equals mCp delta T. Now, remember this time I'm solving for the specific heat, so I have to plug in all the other things, including the Q. So, I'm going to start by plugging in the Q. Remember, joules of heat is your Q. So I'm going to put in 2,500 there. That's kind of a bad 2,500. 2,500. Mass, 20 grams. CP, I don't know. That's my X. I don't know. Change in heat, again, they just came out and told me that it went up by 12 degrees. So, this is my unknown. What I suggest you do is go ahead and multiply these two together, all right? And you're going to get 240 CP. 20 times 12 is 240, and then there's your CP. This is one variable. It's just got 2 little things there. Equals 2,500. We're going to divide that 240 out, so we'll isolate that specific heat variable right there by itself, 240. And then we're just going to divide that. So I'm going to say 2,500 divided by 240, and I get 10.4. 10.4 is the specific heat, the CP, as we say, for specific heat. Now, I made this problem up so these numbers aren't real and they don't really apply to any certain substance. But what I could do, and I will do probably, is once I ask you to find the specific heat, is I might really make it for a real substance on this page. So if I ask you to identify what this unknown substance is, then you could simply look and compare it to the specific heats on the front cover and pick out which one matches the substance, okay? And identify what it is based on what has that specific heat. Okay, we only got 2 more problems, children. So remember, that formula, Q equals mCp delta T, focuses on warming something up or cooling something off, changing the temperature, but not trying to melt it or vaporize it. So what if we are trying to melt or vaporize something? It takes heat to do that. So let's do one of these problems. How much heat energy is required to melt 12 grams of ice? Okay. Well, I go back to my melting formula, all right? Q, which is how much heat, the heat energy, mass of the ice, and remember, this is the constant that we get off the front cover that's set every single time you solve a melting problem. You just simply plug in the 334 for the HF, which is the heat of fusion, fancy word for melting. All right, so what we're going to do is we're going to use the melting formula, all right? And I want to know how much heat energy. Well, that's that right there. How much heat energy is the Q? M is the mass, and I have 12 grams of ice. And heat of fusion, notice that they didn't give it to you, but if you know to use this formula, you know you have to plug that in. And again, that's a constant. That is 334 every single time you are melting. So we're going to say 12 times 334. And I get 4008. And again, keep in mind that that is joules, okay? But that's a lot of joules. That's a big number. So rather than having to deal with 4,000 something joules, I'd rather say that that is simply, Beyonce it, 1, 2, 3, 4 kilojoules. Why not? Okay? I mean, you could say 4.008, but you could say 4.008, but what's the point? We want to make it shorter. So there you go. Last problem of the day. What if I were to ask you something like this? How much heat is needed to convert 50 grams of liquid water into steam? Now, notice I didn't use the buzzword vaporize, but we should know that converting liquid into steam is vaporization. So although I didn't use the word, we need to be thinking, oh, I'm vaporizing it. Water to steam, vaporization. So because I know I'm vaporizing, I'm going to use the vaporization formula, which is just like the melting formula. Instead of the HF, we got the HV, okay? It says how much heat energy, so I'm solving for Q. I need the mass of the water, which is 50. And HV, again, is a constant from your front cover of your reference table. You just simply plug in the 2260. We're going to multiply those. Obviously, that's going to be a pretty big number that I would want to report in kilojoules. So I've got 113,000 joules. Because remember, every time we solve for this Q, it's spitting it out in joules. Well, ain't nobody wants to deal with that much. So what we're going to do is we're going to either divide it by 1,000 or we'll Beyonce it, and it's going to become 113 kilojoules. And that's probably how I would ask you to report that. All right. If you have any questions, please contact me. Anytime you would want to raise your hand, I want you to pick up your phone, text me, and we can have a one-on-one meeting and I can answer your question. I can help you through these and we can work them out together, okay? Peace. See you later.